morning. I'm Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today, I'll be taking a lecture on microwave spectroscopy, or it is also known as rotational spectroscopy. Now, if we see the different regions of electromagnetic radiation, then electromagnetic radiation, it starts from gamma rays, high frequency, that is gamma rays, up to the radio waves. If I see where my rotational spectrum will be observed, then it is going to be observed in the microwave region. Here you can see the microwave region, and the wavelength in the microwave region is from 1 centimeter to 100 millimicron. Up to this region, up to this wavelength, we can study the rotational spectra, or we will observe the rotational spectroscopy. Now, the electromagnetic radiation, in the electromagnetic radiation, this is the direction of the wave, and here you can see that the electric and the magnetic fields, they are aligned perpendicular to the direction. So, electric and magnetic fields are produced which are perpendicular to each other. Now, the interaction of radiation with matter. Different radiations, they interact differently with matter. For example, the X-rays, they are able to cause ionization. Then the ultraviolet radiations, again they can emit or exit the electrons. We can study the pi electrons. In the visible range, we can study again the electron, the pi electrons can be studied. In the infrared radiations, we can observe the molecular vibrations, and in the longer wavelength side, that is the microwave side, we can observe the molecular rotation or the torsion. Now, here I am showing the rotational spectrum of CO at 40 Kelvin. Now, here in the rotational spectrum, you can see that the lines which we are observing, they are equally spaced, right? And now we will learn why the spacing of these lines, they are equal, but they vary in intensity. The intensity is varied. So, why they vary in intensity, I am going to discuss. And this spectra, it is utilized for finding out the bond length and even the bond angles of the molecules. Now, coming to microwave spectroscopy, what exactly it is. Now, this rotational spectroscopy, it involves the transition between the rotational energy levels of a gaseous molecule having permanent dipole moment on the absorption of radiation which is falling in the spectral range from 1 to 100 centimeter inverse in the microwave region. Now, we study these transitions only in the gaseous molecule. Why? Because in gaseous molecules, we can observe free rotation. In liquids and solids, the bond is strong, therefore, there is no free rotation, but in gaseous molecule, we can observe free rotation, therefore, the energy levels are quantized in the case of gaseous molecules. And this spectroscopy, it is shown by molecules, those having permanent dipole moment. Those molecules which are homodiatomic molecules or having center of symmetry, they are not going to be microwave active, or they are not going to show any spectra in the microwave region. Now, coming to the mechanism, how the absorption of electromagnetic radiation, it takes place in the microwave region. Now, a molecule which is having permanent dipole moment, it generates an oscillating electric field on rotation. Here I am taking the example of HCl molecule. Now, in HCl molecule we can see that there are permanent dipoles. H is delta positive, Cl is delta negative. So, there is permanent dipole in this molecule, and when this molecule rotates, it is going to produce an oscillating electric field. And when this field generated by the electric field generated by the rotating molecule, it becomes equal to the electric field of the radiation, then a resonance occurs, and at that resonance the molecule can absorb the microwave radiation, and it is going to show the absorption microwave spectra. Or when the oscillating electric field produced by the molecule or the component of the dipole of the molecule, it becomes equal to the energy which is being supplied by the radiation source. Again, if this molecule is in the higher energy state, it can lose energy and move to the lower energy state, and then we can observe the emission microwave spectra. What happens here? The oscillating electric field, it is produced by rotation. How? Now, here you can see H and Cl. H is positive, delta positive, and Cl is delta negative. Now, I am showing here it is H and this is Cl. When H and Cl are in this position, then the component of the dipole, obviously it will be in the direction of Cl minus, because Cl minus is going to attract the electron. Therefore, the component of the dipole will be towards Cl minus. If Cl is on this side, left side, and H is on the right side on rotation, rotation can be this way or it can be in this way. So, if Cl is on this side and H is on this side, then the component of the dipole will be on direction will be this direction. Again, when Cl is above, H is down, then the component of dipole will be in this direction, above direction. So, as the molecule is showing different rotations, our component of the dipole is also changing directions along with it. So, this is the direction of rotation, how it is rotating. This is the direction of the dipole. Again, I will explain. Here H is positive, Cl is negative. So, here H is positive, Cl is negative, partial negative. So, the direction of the dipole will be towards the Cl minus ion. Similarly, the direction will always be towards the more electronegative atom, and as a result, the rotation or the fluctuation of the dipole moment, it will be measured in a particular direction. This, the component of the dipole with respect to time, we are going to observe the crust and the trough. Here we are observing the crust and the trough. So, the rotation of the polar diatomic molecule showing the fluctuation in the dipole moment, it is measured in a particular direction. Now, this oscillating dipole, it can be provided by the rotation of a permanent dipole, like example I have taken already HCl. And when this type of molecule having permanent dipole, it rotates in the microwave region, then on interaction with the radiation, it leads to the generation of microwave spectra. So, again I will repeat, the molecules having permanent dipole, they produce oscillating electric field on rotation, and when the rotation of the molecule, the frequency of rotation of the molecule becomes equal to the frequency of the radiation source, then only the molecule can either absorb microwave radiation and it can move from the ground state to the excited state. This is the absorption microwave spectra, or if it is already in the excited state, higher energy state, it is going to lose energy. It is going to lose energy and then come back from the higher energy state to a lower energy state. Then it will show the emission microwave spectra. And why only those molecules having permanent dipole moment? Because only those molecules can produce the oscillating electric field, because there are going to be partial charges on the atoms or in the molecule. There will be permanent dipole in the molecule, and the direction or the vertical component of the dipole, it is going to change its direction as the molecule changes its rotation. Now, here the incident electromagnetic waves, they can excite the rotational levels of molecules provided they have an electric dipole moment. The electromagnetic field, it exerts a torque on the molecule. The spectra for rotational transitions of molecules is typically, it is in the microwave region of the electromagnetic spectrum. Now, here I am showing how the electric field in the electromagnetic wave, it is exerting a torque on the electric dipole. How it is showing? The positive and the negative charges here, and the way it is exerting the torque in the electric or on the electric dipoles. Now, the absorption of microwave radiation, it causes heating due to the increased molecular rotational activity. When the molecule is going to rotate, then the molecule will get heated, or the radiation, it is going to cause heating in the molecule, and that heating is sufficient to cause the rotation of the molecule. Now, as I have already said, the homonuclear diatomic molecules, because they do not have any dipole moment, they have zero dipole moment and have zero change in dipole during the rotation. Hence, they do not interact with the radiation. As a result, homodiatomic molecules are microwave inactive. Similar is the case with molecules having center of symmetry. Molecules having center of symmetry, this molecule has center of symmetry. As a result, again this molecule is going to be microwave inactive. Then heteronuclear diatomic molecules. Heteronuclear, I have already taken the example of HCl, HF, NO, CO. They have permanent dipole moment. They are polar compounds. As a result, and they also show the change in dipole during the rotation. Hence, they interact with the radiations in the microwave region. As a result, they are going to be microwave active molecules. Now, how we get the rotational spectra in the case of rigid diatomic molecules? Here I have taken two atoms. Here are the two atoms, and their masses of the first atom is m1 and mass of the second atom is m2, and the internuclear distance between the two atoms is r0. Here I am showing with r0, and this is the imaginary axis passing through the center of gravity, and the molecule should rotate in such a manner around the center of gravity that their position of center of gravity should not change. This r1 is the distance of molecule m1 from the center of gravity, and r2 is the distance of the molecule m2 from the center of gravity. So, we are taking a molecule which is going to behave like a rigid rotor. Here on rotation the center of gravity will not change. Now, here we are considering only rotational motion of the rigid diatomic molecule, and a diatomic molecule can rotate around a vertical axis, and the rotational energy levels is quantized. We are taking a gaseous molecule, therefore, the rotational energy levels are quantized. Now, for rotation about the center of gravity, their moments should be equal. That means m1 r1 mass of first atom into the rate distance should be equal to m2 r2, and we are going to assume the bond is a rigid bond, and this internuclear distance r0 is equal to r1 plus r2. So, from this equation we can find out that r2 is equal to r0 minus r1. So, we are going to put this value of r2 in the above equation. When we are going to put this value of r2 in the above equation, our first equation becomes m1 r1 is equal to m2 r0 minus r1. Now, similarly, we can find out the value of r1. r1 will become r0 minus r2, and we will put this value of r1 in equation 1. So, we are going to get m1 r0 minus r2 is equal to m2 r2. So, our r2 will be calculated, we can calculate as m1 r0 divided by m1 plus m2. So, the moment of inertia about the center of gravity, the moment of inertia is given by m1 r1 square plus m2 r2 square. So, we have already calculated the value of r1 and r2. So, the moment of inertia will become m1 m2 r0 divided by m1 plus m2 whole square plus m2 bracket open m1 r0 divided by m1 plus m2 bracket close whole square, or it is going to become, if we calculate, it will become m1 m2 divided by m1 plus m2 r0 square, and this m1 m2 plus m1 plus m2, m1 m2 divided by m1 plus m2 is nothing but reduced mass. So, as a result, our moment of inertia is going to become equal to mu r0 square. Now, a diatomic molecule, it can rotate around a vertical axis, and the rotational energy is quantized. In the case of gaseous molecules, the moment of inertia is used to calculate the rotational energy levels of rigid diatomic molecule. By using the Schrodinger equation, the different rotational energy levels allowed to the rigid diatomic molecule, they are given by the value Ej, where this J, Ej energy of the rotational value is equal to h square divided by 8 pi square I capital J bracket open J plus 1 bracket close joules, where this J is nothing but the rotational quantum number, and it can have the values starting from 0, 1, 2, 3 up to high values, where I is the moment of inertia, and this Ej, it is the rotational energy. This Ej is the rotational energy of rigid diatomic molecule in joules. H is the Planck's constant, pi again 3.14, 22 by 7 is the value. So, the energy the rotational energy level or the rotational energy of diatomic molecule is equal to h square divided by 8 pi square I multiplied by j into j plus 1. Now, to convert the rotational energy which is given in joules into wave number, we can use the equation E is equal to h nu. H is the Planck's constant and nu is the frequency. Since the energy is quantized, now we can specify the energy by specifying any one of the following. The frequency n per second E is equal to h nu. In terms of wavelength, E is equal to hc by lambda. In terms of wave number, where wave number is inverse of wavelength 1 by lambda. So, here E is equal to hc multiplied by wave number, or wave number is given by energy divided by hc, where h is the Planck's constant and c is the velocity of light. So, from this equation we get that wave number is equal to energy by hc. So, the rotational energy levels for a rigid rotor, putting the values, the last wave number is equal to energy by hc in this equation. In the equation where we have found Ej is equal to h square upon 8 pi square I multiplied by j into j plus 1, we get Ej is equal to this rotational energy level is equal to Ej upon hc is equal to h upon 8 pi square Ic multiplied by j plus 1. The value which we have calculated of wave number, putting it in the for the calculation of Ej. So, again the value of j is can be from 0, 1 to rotational constants, rotational quantum number, sorry. Now, from this equation, this h upon 8 pi square Ic, they are generally the constants for a specific molecule, and this has been given the value of B. B is the rotational constant, where B is equal to h upon 8 pi square Ic. So, substituting this entire value by capital B, because for a particular molecule its mass, radius or moment of inertia is going to be fixed. Therefore, we can substitute these values by capital B, which is the rotational constant, and hence our equation becomes Ej is equal to Bj multiplied by j plus 1 centimeter inverse in terms of wave number. Now, if we put different values of j now, we can calculate by changing the value of j, we can calculate the different values of Ej. How? Here, if I put the value of j as 0, j is 0, then I will get, put this value 0, 0 plus 1 and multiplied by 0. So, our Ej value will become 0. If j is 0, anything multiplied by 0 will become 0. If j is 1, if I put j 1, so 1 plus 1 2, 2 multiplied by 1 2, 2 multiplied by 1 2 into b. As a result, if my j is 1, my bj j plus 1 will become 2b. If I put the value of j as 2, if I put here 2 and 2 here, so 2 plus 1 3, 3 multiplied by 2 6, so my Ej value will come out to be 6b. Similarly, we can get, by changing the value of j, we can get different values of Ej. And in the case of rotational spectroscopy, the selection rule is that the j delta J can be either plus or minus 1. Delta J can only be from one rotational level, you can move from to the other rotational, second rotational level. It is not that you can keep on jumping the rotational level. From first rotational level, you are going to move to the second. From second, you are going to move to the third. It is not that directly from first rotational level, you can move to the third rotational level. So, for the pure rotational spectroscopy, the selection rule is delta J is equal to plus minus 1. For absorption of radiation, it is plus 1, and for emission of radiation, the value of delta J can be minus 1, or it is minus 1. Now, that is in general the transition takes place from J to J plus 1. The energy gap between two energy levels, or rotational frequency between two energy levels. The energy gap between two energy levels is given by variation in energy delta E is equal to Ej plus 1 minus Ej. This is the lower level and this is the next higher level. So, from low level to the higher level or from higher level to the lower level, the energy difference will be given by Ej plus 1 minus Ej. Now, here Ej is given by, you can see Ej is given by Bj j plus 1. So, Ej plus 1 will be given by, here Ej plus 1 will be given by Bj plus 1, here Ej is given by Bj j plus 1. So, Ej plus 1 will be given by Bj plus 1 into j plus 2. So, the higher energy level, here in both the cases we are going to add plus 1, only then we are going to calculate the higher Ej plus 1. Ej plus 1 will become when we add 1 and 1 in at both the j positions. So, it will become Bj plus 1 multiplied by j plus 2. So, here you can see Ej plus 1 will become B multiplied by j plus 1, where it was only j, it is going to become j plus 1 because we have increased one level, and where it was j plus 1, it is going to become j plus 2. Again we are going to add 1, and Ej will remain same, it is B multiplied by j plus 1. So, on calculation of these, we are going to calculate, or we will get the energy gap, it is going to become 2Bj plus 1. So, on changing from j to j plus 1, our wave number, it changes from 2Bj plus 1. So, the energy difference is going to be given by 2Bj plus 1 centimeter inverse. So, here on moving from 0 rotational level to the first, 0 to first, it is going to become 2B. 0 plus 1, 1 multiplied by 2B, it is going to give you 2B. On changing from 1 to 2, it is going to become 4B. On changing from 1 to 2, it is going to become 4B. From changing to from 2 to 3, it is going to become 6B. On changing from 1 to 2, 1 plus 1, 2, 2 multiplied by 2, 4 into B. On changing from 2 to 3, 2 plus 1, 3, 3 multiplied by 2, 6. So, it is going to become 6B. So, here you can see from changing from one level, rotational level, to the next higher level, we are getting the energy difference as 2B, 4B, 6B, 8B, 10B. A difference of 2B is observed. 2B, 4B minus 2B, again it will be 2B, again 6 minus 4B will be 2B. So, we are going to get these different energy gaps. Now, the frequency separation, the outcome of it is the frequency separation between adjacent lines. The different lines that we are going to observe in the rotational spectra, they are going to be at a distance of 2b, because here at every level, if we see from one level to the another level, the difference is of the 2b. Therefore, the frequency separation in the rotational spectrum will be observed, or the lines are going to be observed at a difference of 2b. The frequency separation is constant, that is 2b centimeter inverse, whereas rotational energy, it is going to go on increasing. The separation lines will be at a constant value, but the intensity of lines will go on increasing. Now, here coming to the rotational spectra of rigid diatomic molecule. So, for a rigid rotor on transition from J to J plus 1, we have observed it is going to be 2b J plus 1. So, if J is 0, then Ej is 0. If J is 1, then Ej is 2b. If J is 2, our Ej will become 6b. So, the energy, these are the allowed rotational energy levels in the rigid diatomic molecules. So, we are going to observe a rotational spectra, we are going to observe a peak at 2b, then 6b, then 12b, then 20b, then 30b, and the difference between these peaks is going to be only 2b because it is constant. Now, here I am showing how on transition from one level to the other level, we can see that the energy is increasing. The energy keeps on increasing, but the distance between the two lines, it remains the same. So, these are the allowed rotational energy levels, and between the allowed rotational energy levels, we see that the lines, equally spaced lines, are going to be observed, and this spacing is going to be fixed, that is of 2b. Now, rotational spectra of rigid rotor. Apart from the specific rule delta J is equal to plus minus 1, there is another rule that the molecule, it should have a permanent electric dipole moment mu. Thus, homonuclear diatomic molecules, they do not have a pure rotational spectra, and whereas the heteronuclear diatomic molecules, they are going to show the rotational spectra. The allowed transitions are delta J plus minus 1, delta J is plus 1 for the absorption, and delta J is minus 1 for the emission rotational spectrum. Now, here again I am showing the same diagram. Here the lines, they are spaced equally at the distance of 2b, and these are from changing the value of J from 0 to 1, from 1 to 2, 2 to 3, we are getting the different energy levels, allowed rotational levels. When J is 0, energy is 0, when it is 1, it is 2b, when it is 2, J is 2, energy is going to be 6b, then 12b. So, we are going to observe peaks at 2b, 6b, 12b, 20b, 30b, and the distance between the lines will be 2b. So, this is the rotational spectra. Here are the different rotational energy levels. Now, the molecule require very less energy for the translational movement, and energy required for the translational movement is very less, and if you provide some more energy, then the molecule, it starts rotations. So, we are going to see rotational. This is the vibration transitions, these are the different vibrational levels. This is the vibrational levels, and in each vibrational level we can see a number of rotational levels. So, for each vibrational level there can be a number of rotational transitions which we can see in the microwave region. Coming to the applications of rotational spectroscopy, by using rotational spectroscopy we can determine the bond length of a polar molecule. We can also determine the symmetry in a molecule. We can determine the dipole moment of gaseous molecule, and we can also do the chemical analysis of a substance. So, these are the various applications of rotational spectroscopy. Thank you.